Hey everyone, we are doing dot point 3.2 of electromagnetism, and we are looking particularly today at Faraday's law and Lenz's law, um, two really critical but kind of complicated concepts. Let's start with Faraday's law. It says that when a conductor experiences a changing magnetic field or changing flux, then it will produce an EMF will be produced in it, or an electromotive force, which is often a voltage, um, and will often cause a current. There are sort of three different ways of thinking about it. Change in flux will produce EMF, change in flux will produce voltage, change in flux will produce a current. But really, it always produces an EMF, which most of the time is a voltage, which a lot of the time will create a current. It's sort of the same thing, but a little bit not. Um, okay, and the amount of so that's why we spent the last video talking about changing magnetic flux. So for example, if you had a magnet moving away from a wire, here's our wire, it's a loop of wire. Right now, the magnetic field is going into the wire, but as the magnet moves away, less and less flux is in the wire, okay? And the amount of EMF you get is going to be equal to, well, it's going to be proportional to how much the flux is changing and what time frame it happens, okay? So moving the magnet away really quickly is going to increase the amount of flux, and also having a stronger magnet creating a bigger change in flux, that's also going to change the amount of EMF produced as well. N here is saying how many loops of wire you have that are being influenced by this change of current. So here I've got a single loop, but it could be 2, 3, 4, 5 loops, all part of a solenoid or something like that. Each loop you have adds to that electromotive force. That's why in a lot of electrical devices you'll see wires curled up around hundreds of times. That's to increase the amount of EMF you get, or sometimes it's to increase their strength as a electromagnet. Works the same sort of way. Okay, so that is Faraday's law. He discovered it by doing exactly this. He had a solenoid, he had a magnet, he moved the magnet in and out. The solenoid was connected to a galvanometer, which is kind of like a microammeter, and he could see the current being generated through his device there. Okay, relative movement between magnets, straight conductors, metal plates, and solenoids. So you kind of need a complete circuit. You definitely need a complete circuit to generate a current. So in this case, this is a complete circuit. Current can flow around these wires and around through the galvanometer. It's a complete circuit, right? If you have a sheet of metal experiencing the change in flux, right? It's a sheet of copper. That sheet of copper can also have complete currents going around through it, okay? But this is different to just one length of wire. So one length of wire can have EMF. EMF is okay, but it's not going to have a current. A current's not going to be possible inside just one piece of wire like this that's not connected to anything else. So we have straight conductors, metal plates, and solenoids. Let's now talk about Lenz's law. Lenz's law, because that's another beast entirely. Now, Lenz's law is going to tell us what direction the current is going to flow and why. Let's think about this situation again, but let's limit it just to a single wire experiencing the change in flux. And actually, to make it even easier again, we're going to look at as if the magnet was coming towards the wire. There we go. Okay, we've got our lines of flux here. All right, Lenz's law says when a conductor experiences a change in flux, it is going to have a current induced in it, and that current is going to produce its own magnetic field that opposes the change in flux. What do I mean by that? So here we have a change in flux. There's not much flux going through the wire, and then as the magnet comes closer, there's going to be more flux, okay? So as the magnet comes closer, we're going to get more flux going into the wire here. How can this conductor oppose that change? It can oppose it by creating its own lines of flux in the opposite direction, which will cancel out the original lines, making it more like what it was to start. So it started with not much flux. As the flux increased, it's going to counteract that, decreasing it, bringing back to the beginning. Okay, I'm saying this very precisely because it's not always intuitive the way this works. So how is it going to produce a line of flux in that direction? Well, we use the right-hand grip rule. Now, previously we've talked about the right-hand grip rule for a current in a wire like this. Thumb is the direction of current. Your fingers curling around that wire are going to tell you what the direction of current is. So in this case, the current is, fingers are going to be magnetic field. So in this case, magnetic field is going to go into the page underneath it, around the back, out of the page on top, and across the front. So into the, where's my mouse? Into the page down the bottom here, boom. It's going to go around the back, up like this. Yep, out of the page at the top, and it's going to come across the front like that, okay? Hand goes in, around, and back out. Around there. However, in a loop of wire, when the current is going in a circle, we can flip these two around. In this case, the current in the wires in the solenoid are the fingers, so current's curling around. Thumb's going to point in the direction of magnetic field. A magnetic field comes out of north, so this is going to be the north side, and into south, so this is going to be the south side here. So in the case of my loop of wire here, if I use my right hand, I put my thumb pointing out of the page, which is what this blue arrow is supposed to be representing. Thumb's coming out of the page, my fingers are going anti-clockwise. So the current in this is going to be going anti-clockwise around like that to produce a magnetic field that comes out like this that will oppose the change. Keep in mind, it will only produce current while this magnet is moving. As soon as this magnet stops, this current stops, this magnetic field goes away. Okay, it's counterintuitive if you try this out for the magnet going backwards. So if we have a new situation, so we get rid of that, we get rid of our directions of current, boom, draw everything back in. Now we're saying the magnet's going backwards, right? So we've started off with a lot of flux in this direction, and now as time goes on, that flux is disappearing. Here it is disappearing as that magnet is being drawn further and further away, right? The magnet's going backwards. Now what is this thing going to do? Well, now it wants to produce a magnetic field into the page, into it, to counteract the change. Before there was a lot of magnetic field going into it. Now the magnetic field's going away. To counteract that change, it wants to bring that magnetic field back. It's going to produce it itself. Okay, right-hand grip rule, thumb in the direction of the magnetic field. So in this case, it's into the page. I haven't drawn my into the pages very well. Should be like a cross into the page here. Okay, so now my fingers are going clockwise around it like this. Yeah. Good. That is how Lenz's law works. Last thing here, we need to talk about, where is it? Aha. With reference to energy transfers and transformations. Okay, we're getting electrical energy, but where is that energy coming from? So there's one last thing to think about. If in this situation you have a magnetic field being produced like that, that means that this side, or the side closer to us of this coil, is the south side, and the side underneath the coil, I'm going to draw it over here, is the north side. This south is going to attract the north and vice versa. They're going to put a force on each other, pulling them towards each other. What does this force do? It slows the magnet down. Remember, the magnet's moving away, but now it's being pulled back towards the coil, slowing it down. The magnet is losing kinetic energy. That kinetic energy is being converted into electrical energy. Nothing is for free. If you go back to when the magnet was being brought towards, you would have seen that these poles would have swapped. The north would have been repelling. So as the magnet was being put towards the coil, it would have been repelled by the coil, slowing it down, making it lose kinetic energy, creating electrical energy. That is how energy transformations comes into this. That's how conservation of energy is working in this as well. Okay, last thing we have to do is talk about one solenoid in the vicinity of another solenoid. And to talk about this, I'm going to show you what the original setup was, what Magic Mike himself, and by magnetic Mike, I mean Michael Faraday, what he did. He had a very interesting setup. He had a ring of iron. The iron wasn't a permanent magnet. It didn't have any currents in it or anything like that. He had loops of wire around one side of the magnet and loops of wire around the other side as well. Okay, these loops are insulated wire, so they are not electrically connected to the metal or anything like that. Okay, and on one side of this, he attached a galvanometer to measure if there was any electricity in this. Now, keep in mind, in this wire here, not connected to the red wire, not connected to any source of electricity, no battery or anything. But on this side, he had a source of power and a switch. Okay, what did he find? He found that when the switch was closed, bam, as current flowed through this, that created a magnetic field. If I use my right hand grip rule, I can see that as my fingers curl around this way, thumbs pointing to this side, this would have been the north side, this the south. So that magnetic field would have been coming out this end, going into this end here. Okay, created a magnetic field. Now, for this loop of iron, which is ferromagnetic, that it extended that magnetic field to go around the whole thing like this. Yeah, essentially, when he turned on the switch, the blue coil experienced a change in flux. Okay, now this pink line I've drawn here is magnetic field. It's not a current. The only current is the red down here. So we've created a current here that's connected to the battery. Magnetic field lines, magnetic flux appears around here when we turn it on. That changing field, according to Lenz's law, the blue wire experiencing a changing flux is going to try and oppose that change with its own current, its own flux. So what's blue flux going to do? It's going to try and oppose this change. It's going to try and get rid of this pink magnetic field by making a magnetic field in the opposite direction. That means its current needs to go in this direction. Yep, creating a magnetic field to cancel out the newly created one. And that current is measured in the galvanometer. The galvanometer goes ding, and he could see that when he pressed the switch down here, a current was produced up here. Okay, if the whole thing wasn't attached with iron, it was strong enough, he might notice that they'd repel each other as well, because of the magnetic fields would be pushing against each other. But it's all attached to itself, so it did not move around. Okay, now as the switch was held down, and this magnetic field was just constantly here, the galvanometer went back to saying 0, nothing's happening. It's because there's no changing flux. Even though there is flux there, it's not changing. When you let go of the switch, flux changes, it disappears, and ding, the galvanometer reads again. But then if you keep it off, it goes back to 0. So what happens is you push it on, ding, and slowly to ding, and then as you turn it off, ding, and then slowly back to 0. So it only registers a current when it's being turned on or when it's being turned off, not in between. So on, staying on, no current, but while it's off and staying off, there's no current again. That is what he found. Okay, that was a lot to think about, and it's going to be really, really important for the remainder of section 3. So I guess try and learn it as best you can. Practice it, do examples. One example to think about is what happens if you drop a magnet through a tube of metal, through a conductor. You drop a magnet, what's going to happen in this area above the magnet, which is experiencing a changing flux because the magnet's moving away from it, and what's going to happen underneath it because this area is experiencing changing flux as the magnet's getting closer to it as well. Have a think about that. I'll see you guys next time.